Hey guys, this is Mr. Piercy, and we're going to be looking at today are some properties of chords inside of a circle. We're going to be looking at how chords and the measurements of their intercepted arcs relate and how far apart they are from the center of the circle. Uh, let's go ahead and get into it. There are some demonstration videos that go along with this video that demonstrate why the theorems are actually true. So I would encourage you to definitely go back and watch them at some point if you have not already done so. So the first theorem that we're looking at here, again, theorem 10.3 means absolutely nothing to me, but there's no standardized name for some of these theorems. Even the theorem that I'm providing with the text is not technically an official name, but I like it better than simply saying theorem 10.3. So here we're talking about corresponding arcs of congruent chords. Well, the corresponding arcs would be, well, the chords that we're referring to in the diagram would be chord A, B, and chord C, D. Well, their corresponding arcs would be arc A, B, and arc C, D. Well, because the two chords are congruent to each other, it means that the two arcs that they create would also be congruent to each other. Now, of course, we're only referring to the chords actually made by the segments that actually, in this case, the ones that actually do look congruent. We would not really be concerned with these because clearly those are not going to be the same. They're not going to have the same measurement. Uh, but again, you can go back and kind of take a look at the demonstration video that I've made that goes along with this to see how I'm determining those specific chords with the central angles. So moving on, now that we understand that, well, if I have congruent chords of congruent circles or the same circle, then their corresponding arcs also have to be the same. So in this example, we see that circle A and circle D are congruent to each other because they have the same length radius. And what we see here in the second circle, or the circle on the right, arc FE is 125 degrees. Well, we know that the circles are the same because the radius is the same, and we're also provided the segments, the chords are the same because of the hash marks on it. So if arc FE is 125 degrees with a chord that is congruent to BC, then that means the arc here at BC also must be 125 degrees. So that's how we're kind of thinking our way through the problem. And let's go ahead and take a look at our fill in the blank stuff there and go ahead and get them down. And when you're ready, let's move on. Here are a couple of other chords. Now, really, this is just one chord. I'm sorry, no one chord. This is really just one theorem. It's just they wrote it down twice because here they're giving you the theorem, but they're also giving you the converse of the theorem, which also happens to be true. So the one on top says the perpendicular bisector of a chord theorem. Well, basically what that says is if I have a chord of a circle that is being perpendicularly bisected, well, the chord that does the bisecting has to be a diameter. The converse of that says if I happen to have a chord that is if I happen to have a diameter that is perpendicular to a chord, then it also must bisect it. And the second part here is also going so far as to let you know that the arcs, which would be, and I think my pen, yeah, here we go. Let's pick a better color here. It's also letting you know that this arc here and this arc, okay, well, it doesn't matter, that the two arcs would be the same. So we could also include that information here, that because this segment from T to P is congruent to the segment from R to P, then their respective bits of arcs also have to be congruent to each other. Now, this is a really, really good question. I really like the practical aspects of the question that we're seeing here. And again, I'm not going to pay attention to the solution stuff for now. So let's just focus on the stuff at the top and how would we problem solve it. So we have a journalist that's writing a story about these, three sculptures. Maybe they're famous. I don't know. They're writing a story about it. Well, they want to be able to place a camera that's going to be the same distance away from all three of these shapes. Okay, so what we're going to be looking at is, well, how are we going to? I don't want my pen here. I don't want my pen. I keep picking. There we go. Okay, so I kind of like the way that down here at the bottom, they are kind of giving you what I'm kind of giving you. So what they're giving you here and what I'm giving you here are essentially the same thing. But the question is, well, how do we know where to place the camera so that it's the same distance away from all three figures? Well, if it's the same distance away from all three figures, it must be the center of a circle where all three figures are on the circle itself. So what we are doing is we're kind of making two segments between any of the two figures. So here I have AB and I have BC. And what I'm doing is I'm identifying where the perpendicular bisectors of both of those segments would be. And we're creating this new point right here, which you can call D if you want to, or something. Well, that point, based on the last theorem that we were talking about, if I have two perpendicular bisectors, they would be of a chord. They would be uh, they would be the diameters, and wherever the diameters meet, that means that's where the center of the circle is. And so if we do everything correctly, if I create a circle from that center, we can see that it is going to be the same distance away. I'm off just a tiny bit here, but I did most of this just by eyeballing it. I didn't actually measure anything. Okay, but that's what this question is asking you to do. And there is a time on a job site back when, a long time ago, back when I worked as an electrician, when we actually had to do something like this. We had a kind of a circular area, and we needed to know, well, where the center was. And this was a really good way of figuring out where the center of the particular circle was. We just created a couple chords, bisected them, and see where they intersected each other, and there was the center of the circle. So let's go ahead and finish filling in our blanks here so we can see what we need here. And again, this theorem 10.4, well, that doesn't really mean anything. We should really kind of be thinking about it in terms like that. And I don't even care if you tell me the perpendicular bisector of a chord theorem, as long as you can tell me what it actually means. Well, if I happen to have chords that perpendicularly bisect, that are perpendicularly bisected, then those things have to be diameters. Now here we're going to take a look at the converse of it. So in the diagram here in circle E, it's asking us, well, how long is segment BD? Well, BD is a chord of the circle, and AC is the diameter of the circle. Since AC is perpendicular to the chord BD, it must also bisect the chord BD. So that's that converse of the theorem that we had on the previous slide a second ago, and that's what I'm looking at here. So if F to D is 6, then that means F to B also has to be 6, so the whole chord is going to be 12 units long. Now this is kind of the last theorem that we're really going to be taking a look at in this unit, or in this section I should say. Here, if I also happen to have congruent chords, then the chords themselves will be the same distance away from the center of the circle. Now again, we could write the converse of that, saying that if I have chords that are the same distance away from the circle, then those chords have to be congruent to each other. And that's kind of what we're seeing in the example. Here in example 4, they're not, uh, you know, well, let me backtrack a little bit. For some reason, I'm thinking of a different problem. Here in example 4, they're giving us segment AB to be 12 units long, and segment DC to also be 12 units long. So because they're congruent in the same circle, then that means the distance from F to E and from F to G has to be the same. So that allows me to write the equation that says 3x will be equal to 7x minus 8. And from here, we can just kind of solve the equation like normal. Finding the value of x in this case is going to give us 2. But answering the question, what is the length of segment EF? Well, we just plug the 2 back into the expression, and 3 times 2 says that segment EF is going to be 6 units long. At this time, guys, go ahead and pause the video and try working out the solutions to the 3 problems that you see here. And when you're ready, go ahead and hit play, so that way you can kind of compare your answers with mine. All right. So hopefully we have some good answers now. You've done worked out the problems like I asked you to. Now you're just kind of comparing what you have with what I have. Now looking here in problem 1, we have the measurement of arc TV to be 121 degrees. So here, if I'm working this out, I'm going to say this is 121. And because this and this are the same, then that means this chord and this chord have to be the same. So this is also going to have to be 121 degrees. And that's kind of what we're looking at here. Find the measurements of the arcs CB, BC, CB, BE, and CE. Okay. Well, here what we're seeing is that I have a diameter BD that is perpendicular to a chord CE. Well, that allows me to say that from C to A and from E to A, those have to be the same, because the only time a diameter is perpendicular to a chord is if it bisects it at the same time. Well, if segments AE and AC are the same, then their respective chords, their respective arcs also have to be the same. So that will allow me to say that CB, arc CB is equal to arc BE, so 4x will be equal to 80 minus x. So when I solve for x in this case, we get 16. Well, finding the actual measurements of those things, I'm going to take the 16 and substitute it back into each expression and say, well, CB and BE should be 64, which, substituting, we better get the same numbers there. If we didn't, then our value for x is wrong. And overall, CE, 128 degrees. Now here, going back to example 4, what if segment AB was 27 and EF and GF were 7? Well, how long would CD be? Well, let's see, there we go. Well, since AB and CD are both 7, they're the same distance away from the center, then CD would also have to be 27 units long. So that's it for this particular lesson as far as talking about segments of chords, meaning that are lengths of chords. I don't know why I said segments of chords. But if a chord is congruent inside of a circle, it will create congruent arcs inside of or along the circle, and they will also be the same distance away from the center of the circle. And finally, if a chord is being perpendicularly bisected, well, that bisector, the only way it can happen is if it is the diameter of the circle. And we're getting interrupted with an announcement. But that's it for this lesson, ladies and gentlemen. And if you have any questions about anything that you've seen, by all means, let me know what they are. Until next time, ladies and gentlemen, thanks for watching and take care.